Hello students, in previous video we have seen the combined transformation and the area of transformed figure. Now here let's see solid body transformation. Now what does it? To preserve, this is actually for preserving the shape and size of an object. Size of object. Definition of it. The transformation which preserves size and shape of two-dimensional object is called as a solid body transformation. A transformation which preserves size and shape of two-dimensional object is called solid body transformation. Size and shape of the object is preserved if angles and lengths of vectors are preserved. Right? Now a theorem for this: angles and lengths are preserved under two by two transformation matrix TYBSc if it satisfies the conditions: if first a square plus b square is equal to 1, second c square plus d square equal to 1, third AD minus BC is equal to 1, and one more AC plus BD is equal to 0. These four conditions are satisfied, then we can say the angles and lengths are preserved. And if angles and lengths are preserved, then the size and shape of object is preserved. That is, if size and shape of object is preserved, then that is known as solid body transformation. So these are the conditions on the transformation matrix for said to be it is a solid body transformation. Okay, so now let's see one note, a few notes. First, if transformation is pure rotation, if the transformation is pure rotation, then all these conditions are satisfied, means it will be a solid body transformation. So all conditions are satisfied. You can check using a rotation matrix, are these conditions are satisfied or not. Second note, if transformation is pure reflection, if transformation is pure reflection, then determinant of t is -1. And if determinant of t is -1, here it is said the determinant should be 1. So it doesn't satisfy that condition. So it won't be a solid body transformation. Therefore, one vector, it says one vector changes its direction and theta changes to pi minus theta. Due to that, this happens. So angles and lengths are not preserved, right? Third, converse of this theorem, or we can say above theorem, may not be hold. Means sometime it may happen that all conditions are satisfied, but that will be not a solid body transformation, right? So let's see one example here. Determine if the transformation of reflection through y-axis is a solid body transformation. Justify your answer. Okay. Now, which transformation is given? Reflection through y-axis. Here, T is for reflection through y-axis. Our transformation matrix is as such, right? So here, what happened? Determinant of T is what? -1. Therefore, the condition AD minus BC equal to 1 is not satisfied, right? Therefore not a solid body transformation. Right? Now further, the topic is that transformation of homogeneous coordinates and translation. Okay, using any 2x2 transformation matrix, we have been observed that origin cannot be transformed. Origin remains at the same place. Origin cannot be transformed to any other point. To overcome this difficulty, we introduce a homogeneous coordinate. Okay, these are used to transform the origin. These are used to transform the origin, and along with that object X also. Along with that object X. The corresponding process is called translation. This process is called what? Translation. Transformation of an origin that process is known as translation. Homogeneous coordinates of a point xy is given as x dash y dash h, where h is any real number. And the corresponding plane is called as hyperplane. Here this P is what? xy. It can be written as x dash by h, y dash by h, and 1. Therefore, what is x? X will be x dash upon h. Y will be what? Y dash upon h, where h equal to 1 is the hyperplane. That is the plane in which transformation performed. Plane in which the transformation is performed. Now, note that first, homogeneous coordinates of a point are not unique. As we can take any value of h here, any real number, that's why these are not unique. Okay. Second note says, for homogeneous coordinates the transformation matrix T can be written as A, B, C, D. This is as it is. Simply here we will write 0, 0, 1. Here also 0, 0 as such. Therefore, P star will be P into what? T. So, that is what? P is what? X, Y, and we will write 1. And here AB 0, CD 0, 0, 0, 1. Okay. So, this gives us, this is AX plus CY, BX plus DY and 1. Geometrical effects of A, B, C, D are as usual. Third, for T equal to A, B, P, C, D, Q, L, M, S. Here it will be partitioned as such. Geometrical effect of, here the geometrical effects of L, M, P, Q, S are different. Note this here, this one you should note about it. Okay. Now, translation. You know what is translation? Shifting of an origin with X, that process is known as translation. It is a transformation which changes the position, of an object, in straight line path. Position of an object in straight line path. Okay. Now, translation in XY direction, by factors L, M respectively, that matrix will be, translation matrix can be written as 1, 0, 0, 0, 1, 0 and L, M, 1 as such. Okay. Now, let's see few examples on this. Example, develop matrix what is that? A, reflection through line y equal to 0. That is what? X-axis. Second, shearing in X and Y direction by 3 and -4 units respectively. Okay. Third, translation in X direction by -5 units. Okay, here translation occurs, that's why we need to use the homogeneous coordinates, right? So due to that, this previous two transformation matrix also we will write in 3 by 3 form. Actually these are 2 by 2 transformations, we will write them in 3 by 3. So solution, here what is T? T will be, first T1 is for reflection, right? Then next T2 is for what? Shearing. Okay, and T3 for translation. It will be for translation, right? As such. So let's write them, these matrices. Reflection through y equal to 0 will be what? 1, 0, 0, -1. That is x-axis. Reflection through x-axis. And these one we will write as it is, right? Now, to shearing in x and y direction by 3 and -4. So 1, -4, 3, 1. In here 0, 0, 1, 0, 0, 1. Homogeneous coordinates. Now translation matrix, translation in x direction by -5 units. So 1, 0, 0, 1, this is as it is. Translation is from L and M. So L, x direction will be L, y direction will be M. So here our -5 comes. Here 0 and here 0, 0, 1 as it is. And this product will be 1, -4, 0, -3, -1, 0, -5, 0, 1. You can check your answer. This is our required matrix here. Next example. First, reflect the point P having the coordinates 10.5, 7.3 through x-axis, and then translate in x and y direction, x and y directions by -6.5 and 15.7 units respectively. Okay, solution. First we have to reflect and then translate. So let's find out first of all the transformation matrix. Here T is what? First is for reflection. Let me denote it by RL, and translation. Okay, so reflection through x-axis. So the matrix will be 1, 0, 0, -1. So 0, 0, 1, 0, 0, 1. Okay, and translation is 1, 0, 0, 1 as it is. Translation, so here 6 -6.5 and here 15.7 and 0, 0, 1. And this product is 1, 0, 0, 0, -1, 0, -6.5, 15.7 and 1. This product will be this one. So this is a transformation matrix. Therefore, the transformed point P star having the coordinates which get by applying T on P. P can be written as 10.5, 7.3 and 1 into T. What is T? 1, 0, 0, 0, minus 1, 0, minus 6.5, 15.7 and what? 1. This product gives us the position vector matrix 4, 8.4 and 1. This is the answer here. So point P will transform to P star having these coordinates. Therefore, I can write simply P star is this 4, 8.4. Okay. So as such, the translation matrix can be used. Now, the next thing, let's see inverse transformation. Inverse transformation. Now, sometimes we require to remove the geometrical effect created by T. This can be done, or this can be achieved by using inverse transformation. Inverse transformation, that is T inverse. Inverse transformation, that is T inverse. Now, let me write T and T inverse for some basic transformation. Here T and let it be T inverse. So first, let me write for scaling. For scaling, what is T? T is A 0 0 0 D 0 0 0 1, right? T is this. What is T inverse? T inverse is 1 upon A 0 0 0 1 upon D 0 0 0 1. This is T inverse for scaling. Then second, reflection. For reflection, T and T inverse are same. T will be what? 1 0 0 0 minus 1 0. If it is through x-axis, then it will be same for T inverse also. And if through y-axis, then that is again same. Okay. Now the next one, rotation. For rotation, you know T inverse is nothing but T transpose. That's why it is an orthogonal matrix. So T is here cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, 1. And T inverse is what? Cos theta, sin theta, 0, minus sin theta, cos theta, 0 and 0, 0, 1. That is nothing but T transpose. T transpose, right? Then fourth one is what? Translation. The translation having a T is 1 0 0 0 1 0 x1 y1 0 x1 y1 1 will be there, sorry, 1 is here, remember it. Then T inverse is what here? 1 0 0 0 1 0 minus x1 minus y1 and 1. This is about the inverse transformation. So here we will stop for this video. In next video we will see the rotation about an arbitrary point and reflection through an arbitrary line. These are again two important topics that for that one we need translation as well as inverse transformation. Remember them. Thank you.